All right, today we're going to cover section 3.4. This is variation in multivariable functions. So these are kind of the functions that don't fall into a specific category like the x to a power ones. These are ones that kind of share a similar trait versus a similar formula. And that similar trait is usually how they're related to each other. So we'll cover three different types of variation, and then that kind of gets combined together when we do multivariable functions, and we talk about how they are jointly, or how some things can be have this multiple faceted part where there's a direct variation with this one particular variable and there's an inverse variation with another, something like that. So direct variation is kind of still in that x to a power, but it's a very specific version of the x to the power. It's kind of like if you think about, say you're consistently driving at 60 miles per hour. Every hour you travel, that's 60 miles that you go. So if you travel for 2 hours, you go 120 miles, 3 hours, 180 miles, so on. So that's what you would think of as like a direct variation. One thing increases and another thing increases, or one thing decreases, another thing decreases. Like, to go back to the car analogy, the amount of gasoline in your tank is directly has a direct variation with how many more miles you can drive. As the gas in the tank goes down, so does the amount of miles that you can drive. So if we talk about something being directly varying, we would just typically say that it's y equals some constant that we use as k. K and c are your two typical variables for constant. And so if two things vary directly, we say that it varies in this kind of y equals k times x to the n formula. So an example from physics is Hooke's law. And it says the force exerted by a spring in a scale varies directly with the distance that the spring is stretched. So if a 5-pound mass suspended on a spring scale stretches the spring 2 inches, how far will a 13-pound mass stretch it? So first of all, we've got our equation. So the force should be directly proportional to how far it's stretched. Now, if you wanted to say F equals Ks, where S was the variable, that works too. But usually, you can just think if you want to leave Y and X, that works fine. But don't get super comfortable with that being the only thing you're familiar with. What hurts a lot of people is Y is the function, X is the variable, and that's all they've ever seen. But as soon as I throw a function like f of s equals k times s, that might could throw someone off because they've never seen s used as a variable. Or sometimes you might think of time as a variable as well. But typically what's going to happen is typically you want to name the function by what's being influenced, or sorry, not what's being influenced. You want to try and name functions in a way that makes sense. Typically, like if it's the amount of money you're making, it might be like P of X, where P stands for profit. Some things, though, I'll just say this. Most of your life, I would say probably 99% of the time, you will never see K or C used as variables. And some programs even prevent you from assigning those as a variable just because they're so commonly used as constants. So don't get too caught up, or I would not say don't get too caught up, but don't let just the idea of y has to be the function, x has to be the variable, be the only thing that you ever think of. You can use different things. And a lot of times you will encounter other functions. But now what we've done is, to go back to this one, we know that since it has a direct variation, then it's pretty easy to see that it's going to vary, or it makes sense that it varies directly. If you put a heavier weight on it, it should extend more. So right now, what we have are these two particular things. We know that a 5-pound weight will stretch the spring 2 inches. Now note, or 5-pound mass. I'll just say weight. So if you look at our formula, this is the case. This is our force. And this is the amount of distance it's stretched. So what that allows us to do, so if we know that F is equal to K times S, or K times X, to go with this, then that means I can replace the force with 5, and I can replace the amount that it was stretched with 2. And what that does is now I actually have what my constant K is. It's 5/2. And so by only knowing one instance, we've created a function that will measure it for any instance. So our function in this case is F equals 5/2 of X. And so with only one kind of snapshot, you would say, you now have a function that represents any of these, or any amount of weight. Now, it does make sense though. If you let x be 0, it's not going to stretch the spring at all. And then as x gets larger, it would go on. Now, the hardest thing to do sometimes is just keep a rational mindset that this is a real world problem that you're using mathematics to solve. The largest fallacy you will see a lot of times is people that don't take the domain idea into account. Because you say, oh, I've got a function, it's F equals 5/2 X. And then people start plugging in negative values. You can't hang a negative weight. A negative weight is like reducing tension. So in this case, just keep that in mind in the idea. So, and this is kind of, you can see how much the spring stretches from its original state. And so to go back, so now we have F equals 5/2 of X. And it wanted to know how far would the spring stretch if it had how much would it stretch if it had a 13-pound weight? So 13-pound mass. Now, one other thing to be careful is, where are you plugging in your value? Typically we think of input output. That's still true for a function, or that's true for this function. However, notice the information we're given. We're given how much is or how far will it stretch. X is how far will it stretch. F is how much mass is being placed on it. So 13 doesn't get plugged in for the X value. It gets plugged in for the force value, which is F. So then we have 13 equals 5/2 x. Multiply both sides by 2/5 to get x by itself. And then we're going to have x equals 26 over 5, which is 5.2 inches. Don't forget your units. And so typically for a word problem, you would say a 13-pound mass will stretch the spring 5.2 inches. Now, inverse variation is when it's, instead of k times x to the n, it's k divided by x to the n. So this is when you think of inversely proportional, it's one thing increases, the other thing decreases. Or vice versa. So typically, like, some models will predict, like, as you increase like the price of admission, the amount of people, sometimes you say like there's a turning point where the amount of people, you can increase the price to a certain point before people start leaving or deciding that it's too expensive of an event to come to. So typically at some point, the idea of like ticket cost, that's something that would be inversely proportional. As you increase the price of the ticket, the amount of people willing to attend will go down, because while for some people you could raise the price to $50 and then go, that's not bad, there's some people that go, I can't do 50. But if you were to have the price at 30, they might make it might be more manageable. So that's another one that's an inverse relationship. As the price of tickets decreases, the amount of interest increases. So you can think of that as two sides of the same coin, just depending on which way you look at it. So the weight of a person relative to the Earth is inversely proportional to the square of the person's distance from the center of the Earth. Using a radius for the Earth of 6,370 kilometers, how much does a 180-pound man weigh when flying in a jet 9 kilometers above the Earth's surface? So we have specifically this inverse relationship. So, and again, name your variables things that make sense. W is weight. So it tells us that the person's weight is inversely proportional to the square. So remember, so we have that it's inversely proportional. So that means we're going to have y equals k over x to the n. And when it says the square of the person's distance, that lets you know that n is equal to 2. And so we have our two kind of ideas here. We have the distance, and we have brain work. We have our distance, we have the person's weight. And so now we kind of have how everything is tied together. So, not surprisingly, the weight is equal to k divided by the distance squared. And again, this is an example of naming variables without using your standard y and x. And it's okay to do this. You don't have to always be pigeonholed into y is the function, x is the variable. Use things that make sense. We're using weight and distance, so let's use those. So the radius of the Earth is 6,370 kilometers, and we want to know how much does 180-pound man weigh when flying in a jet 9 kilometers above the Earth's surface. So first thing we're going to do is we just need to know how much does this person, we just need to find that k value first. So if the weight is 180 pounds and the person and the distance is 6,370, Well, you square 6,370, that's going to get you quite a large number. So first thing we have the weight is equal to k divided by d squared. Multiply both sides by d squared. And if you wanted to, this is completely up to you. Notice the first one I solved, I plugged in the values and then solved for k. In this one, I solved for k and then plugged in the values. Either way works out. It doesn't matter. So roughly 7.3 times 10 to the ninth. So our k factor in this case is extremely large. So now we said, okay, if the person is 9 kilometers above the Earth, how much is the person who's 180 pounds going to weigh? Well, now it's just a matter of plugging that in. Because remember, this was your k value. This is the distance, which is 6,370 plus 9, because they're 9 miles above the Earth. So they're about half a pound lighter, depending. Or they're about half a pound lighter being 9 kilometers above the Earth. Now, one thing you would take into account, or you would have to say, is if we went and measured a different person who had a different weight, you would have to recalculate that k value, because beforehand, like with the first example, it told us the weight on the spring and how far the spring stretched. And then we were able just to go on about our day. Because then if you're just increasing the weight of the spring, the weight on the spring, not too hard to deal with. That's going to be, or you think about, you just increase the weight, you increase the weight. In this case, the weight was kind of set in stone. And so when we found this, we end up with something that only works for the distance being the variable. Because we say, okay, well, what if they were, I don't know, 30 kilometers outside or above the Earth's surface, stuff like that. So you have to keep things like that into account. But you can't use this formula to tell the person who weighs 170 pounds. You would have to go back and recalculate k because of that. And so you're only half a pound lighter, so not the best way to lose weight. Now, joint variation is when you have multiple components working together. So, and sometimes you'll hear a joint variation and an inverse variation together. So like it'll vary directly with this and inversely with this. That's an example of kind of a variation of multiple parts. So and typically with this, we pull in z for our main function. And again, powers can change. So the volume of a right circular cylinder varies jointly as the height of the square of the radius. And these are kind of hard to read sometimes. Good Lord. I've been, at this point, teaching college math for about, I'm coming up on my 3rd year, and sometimes I still struggle to read these problems. So the volume of a right circular cylinder varies jointly as the height and the square of the radius. This is why I majored in math and not English. express this relationship in equation form. So it varies jointly with the height and the square of the radius. So we have our height, and it's the square of the radius, so we'll just do r squared. So if these vary jointly, so then v equals a constant times the radius squared times the height. Now this should look very familiar. This is the volume of a cylinder, so K will equal pi. If you were given a volume, a radius, and a height, it should come out to be a rough estimation of pi. If it was not, then you would have a cylinder that is physically impossible to make. Or you're living in a different reality where pi is a different number or a different ratio. And so this is kind of the multivariable function part. So joint variation kind of goes together with multivariable functions. But key takeaway is joint variation means multiple things together. Now one thing to keep an eye out for is, what if it said it varies jointly with the height and the inverse of the square of the radius? Then that means you have a joint variation that is both direct and inverse. So you have one thing that's in the denominator and one thing that's in the numerator. So just be careful as you read through those. And so that'll do it for this one. And let's see, I think we pick up with, we'll do 3.5 next.